Hey everyone, welcome to This Explainer. Today we're diving into something absolutely fascinating that surrounds us every single second of the day. We're going to explore how the very chemistry of materials shapes our everyday lives, and we're specifically looking at this through the vibrant lens of daily life right here in Uganda. From the clothes on your back to the roof over your head, it's literally all chemistry in action.
Let me ask you something. Think about it for a second. Would you ever make a school uniform out of heavy, rusting iron? Or, I don't know, try to build a sturdy house out of flimsy paper? Of course not. We instinctively know that different materials have very specific purposes. But why? Well, that innate understanding is exactly what we're going to explore today by looking at the microscopic structures that make our world actually work.
So here's our roadmap for today. We're going to categorize everyday materials around us, uncover the science of polymers, match properties to their uses, conduct a quick heat test, and finally, tackle pollution and recycling solutions. Let's get right into it.
Section 1. Everyday materials around us. Natural versus synthetic.
Just take a quick look around your immediate environment, maybe the desk you're leaning on or the kadraba you use for your shopping. In chemistry, we actually classify all these materials into two main buckets, natural and synthetic. Natural materials, well, they're exactly what they sound like. Think wood from our forests, cotton from the fields, or clay from the swamps. They come straight from plants, animals, or the earth itself. There are no human chemical alterations whatsoever. They're used just as nature provided them. But then, on the flip side, we have synthetic materials. These are entirely man-made in factories, usually using chemicals pulled from crude oil. We're talking about stuff like polythene bags, nylon ropes, and PVC pipes.
Moving on to Section 2, the science of polymers, building the chain. So, what's the secret sauce behind the strength of these materials? It's all happening way down at the microscopic level. The big takeaway is actually right in the name itself. Poly means many, and mer means parts. Basically, a polymer is this giant molecule built out of tons of tiny, repeating chemical units, which we call monomers, all linked together in a massive, long chain. Picture a beautiful, really long beaded necklace. Just one single bead sitting there on its own? That's your monomer. It's just one part. But when you string hundreds of those exact same beads together, what do you get? You get a long, flexible, super strong chain. And honestly, that beaded necklace is the perfect way to visualize exactly how a polymer behaves at the chemical level. To really lock this concept in your memory, try picturing 10 students standing totally separate in a room. Right now, they're basically 10 individual monomers. But the second they reach out and hold hands to form a long, unbroken line, boom, they instantly transform into a polymer. Suddenly, they're linked up, way harder to pull apart, and they're acting as one giant single unit. So, keeping that student chain in mind, let's talk about who's actually building these chains. Mother Nature is literally the original polymer manufacturer. She makes natural polymers like the cellulose that gives wood its strength or the starch you find in everyday foods like pasho and cassava. Heck, even the protein in your hair is a natural polymer. On the other hand, humans just kinda copy nature's homework. We manufacture artificial polymers in factories, which we generally just call plastics. And that is exactly how we get synthetic polymers like polythene for our bags and nylon for strong ropes. If you want to see the difference between natural and synthetic polymers in real life, you can do a quick tensile strength test. Tensile strength is just a fancy way of saying how hard can you pull this thing before it snaps. Imagine taking a strip of paper, some cotton thread, and a nylon string, all the exact same thickness. Tie them to a bucket, slowly pour water in, and watch the chemistry happen. The paper, which is natural cellulose, is going to break almost immediately. The natural cotton, it'll hold a bit more. But that synthetic nylon, it holds the most water by far before snapping. Human-made polymers have insanely high tensile strength, which is exactly why we rely on nylon for heavy-duty stuff, like towing a vehicle.
All right, Section 3, properties and uses, matching form to function. Now, understanding tensile strength is just one piece of the puzzle. The real magic happens when you see how a material's specific physical property dictates its exact use in our daily Ugandan economy. Take copper, for instance. It's flexible and a brilliant conductor, making it absolutely perfect for umeme power wires. Then you have polythene. It's waterproof and it definitely won't shatter if you drop it, so it's the go-to for Renzeri water bottles instead of heavy glass. Cotton. That's a natural polymer that is soft and absorbs sweat, which makes it perfect for breathable school uniforms on those super hot afternoons.
And cement has massive compressive strength. It can handle massive amounts of weight, making it the literal bedrock of all those multi-story buildings popping up in Kampala. Every single one of these is a carefully calculated chemistry decision. Let's jump to section 4, the heat test, reactions to temperature.
So what actually happens when we expose these materials to extreme heat? If you put them near a heat source like a sagiri, their molecular structures react in completely different ways. Say you gently heat a synthetic polymer, like a plastic basin. Those long molecular chains we just talked about, they start to slide past each other. The plastic softens and melts into a liquid. And that's actually super useful because it means we can remold it into totally new shapes. But if you heat natural materials like wood or cotton, they don't melt. No way. They go through a permanent chemical change. They char, they smoke, and they turn into ash. And finally, if you take soft, wet clay and heat it up in an oven or a kiln, its chemical structure changes permanently. It becomes heat-resistant and turns into a rock-hard, strong brick. And that brings us to Section 5, Pollution and Recycling, Environmental Solutions. Look, synthetic plastics are incredibly convenient, for sure. But that convenience comes with really heavy environmental cost. And first, we need to clear up a major misconception. People always talk about plastic like it's just one single thing. It's definitely not. Plastic is just a broad umbrella term for hundreds of completely different synthetic polymers. The polythene used for bags, the PVC used for water pipes, the polystyrene used for packaging, they all have entirely different, very complex chemical structures. And sadly, all these different types of complex synthetics are making their way into our environment every single day.
400. I really want you to let that number sink in. 400 years. That is exactly how long a single, non-biodegradable synthetic plastic bottle can just sit there, buried in Ugandan soil, without breaking down. Why? Because these are man-made synthetic polymers. The natural bacteria in the soil simply have no idea how to digest them or break them apart.
And this non-biodegradable nature leads to some pretty severe consequences, especially when we're talking about kavira, or plastic bags. When they pile up, they physically block drainage channels, which directly causes those massive city floods during heavy rains. For our farmers, these plastics just sit in the soil, blocking plant roots from growing properly and totally degrading soil fertility. And honestly, perhaps the most dangerous part, when people try to solve the rubbish problem by just burning these bags. Burning synthetic polymers triggers a chemical reaction that releases highly toxic, poisonous gases right into the air we breathe, which can lead to serious respiratory diseases. They should literally never be burned out in the open. But hey, it's not all bad news. There is a very practical, chemistry-based solution here: recycling. Remember our heat test? We know that synthetic polymers, like plastics, melt instead of turning to ash. So we can collect this waste, melt down the old plastics, and actually remold those sliding polymer chains into entirely new, useful things, like sturdy plastic chairs or fencing poles. And the exact same process goes from melting down scrap metal and glass. It lets us turn serious environmental hazards right back into valuable resources. All right, we've covered a lot today. We've seen how the molecular structures of polymers give materials their strength, how their physical properties decide their best uses, and exactly why we have to be mindful of their environmental impact. So I want to leave you with one final kind of provocative thought to test your new chemistry knowledge. Imagine a building contractor decides to build the walls of a house using large blocks of synthetic plastic instead of traditional fired clay bricks. Knowing what you now know about how plastic polymers react to heat, what would be the deadly disadvantages of living in that house in a hot country like Uganda? Just think about those polymer chains sliding around. Keep a close eye on the materials around you, and I'll catch you in the next explainer.